AI-assisted practice prompts. Lesson 66, C# version 11, November 2022. Correctness by construction, generic power, and data clarity. Role definition for this lesson. Your AI assistant acts as a language hardener. It helps you reason about illegal states, expressible intent, and compile time guarantees rather than surface syntax. Practice Prompt 1. Correctness by default, the big idea. Ask your AI assistant. What does correctness by construction mean in the context of C#11? How is this different from relying on conventions, documentation, or runtime checks? Focus on compile time enforcement versus developer discipline. Illegal states versus valid states. Why large systems benefit disproportionately. Outcome. You should be able to explain why C#11 reduces classes of bugs, not just individual bugs.
Sure, in this lesson on C#11, the main idea is correctness by construction. This means that C#11 aims to ensure that many potential errors are caught at compile time, rather than relying on developer discipline, conventions, or runtime checks. The lesson also highlights how this approach reduces not just individual bugs, but entire classes of bugs, which is especially beneficial for large systems. Ultimately, it means the language itself helps maintain correctness right from the start. Absolutely. So here are a couple of C#11 features that illustrate correctness by construction. One, required members. In C#11, you can mark class properties as required, ensuring that they must be initialized before the object is used. This helps prevent incomplete object state. So public class person, public required string name, get init public age. With this, if you try to create a person without setting name or age, the compiler will give you an error. Static abstract members in interfaces. This allows interfaces to enforce certain patterns at compile time, ensuring that implementing classes provide specific static methods, leading to more predictable and safer designs. Public interface and factory create a prop by product to create a product really ensures that every product class implementing iFactory provides a create method at compile time, reducing the chance of runtime errors. These features help ensure that incorrect states or missing implementations are caught before the code runs, leading to more robust and reliable applications.
Practice Prompt 2. The generic math barrier. Ask your AI assistant. Why was generic math fundamentally impossible in earlier versions of C#? What specific language limitations prevented it? Follow-up prompt. Explain how static abstract members in interfaces change what generic algorithms can express. Focus on operators not being part of type constraints. Why where T, struct was never enough. Why this is a language plus runtime milestone. Outcome. You should understand why generic math is foundational capability, not convenience syntax.
Absolutely. Let's break it down. In earlier versions of C#, the idea of doing generic math, basically having generic algorithms that could perform arithmetic on any numeric type, was fundamentally impossible due to how the language was designed. The main limitation was that operators like addition, subtraction, multiplication, and division were not part of the generic type constraints. In other words, you couldn't just say, this type T must support the plus operator in a way that the compiler understood. So for example, if you had a generic method that tried to add two variables of type T, the compiler wouldn't know if T actually supported addition. There was no way to enforce at compile time that T had those operators. The constraint where T, like struct, only guaranteed that T was a value type, not that it supported any particular operations. Now, enter static abstract members in interfaces. This is a big change introduced in newer versions of C#. It allows you to define interfaces that require certain operators to be implemented by any type that implements the interface. This means you can create a generic math interface that says any type T implementing this interface must support addition, subtraction, and so on. This is both a language and a runtime milestone because it fundamentally changes what you can express in generic algorithms. In essence, this makes generic math a foundational capability of the language. It's not just a convenience or syntax sugar, it's enabling a whole new class of type-safe, compile-time check numeric computations that were previously out of reach. Absolutely. Let's look at a simple example to illustrate this concept. Before static abstract members and interfaces, you couldn't do something like this with a generic math operation. So this would not compile in earlier versions of C#. Public T, add T where T is a struct, well, it wouldn't work. The compiler wouldn't know if T supports SPLAS. Now, with static abstract members and interfaces introduced in C#11, you can define an interface that enforces the presence of these operators. So, interface, iAddable, there must be an operator plus. My number is iAddable my number, minus 2 plus 2, provided that equals this. Well, mana equal minus this, or when you say that minus 2 plus 2 is greater than minus 1. So now you can do generic math on any type that implements iAddable T. Public T, AB, where T, iAddable T, is equal to, this is now valid, because T is known to support the plus operator. In this sample, my number implements the iAddable my number interface, which defines a static abstract operator plus. This allows the generic method add T to enforce that any type T used must support addition. It's a fundamental shift because it means the compiler can now ensure at compile time that your generic math is valid, making your code both safer and more expressive.
Practice prompt 3. Thinking in algorithms, not types. Ask your AI assistant. Conceptually, what kinds of numeric algorithms become possible with C#11 that were awkward or impossible before? Focus on algorithms expressed once, reused everywhere. Static type safety without boxing. Numeric libraries and performance-critical code. Outcome. You should start thinking in algorithms over constraints, not concrete numeric types.
Sure. Essentially, what this prompt is getting at is that in CH11, you can write numeric algorithms more generically and flexibly than before. Instead of having to write the same algorithm separately for int, double, or other numeric types, you can express it once in a more algorithm-centric way. The key points are that you maintain strong type safety, so you still get compile time checks and no unnecessary boxing, and you can create numeric libraries that are both more reusable and more performance critical. In other words, you can think more about the algorithm itself and less about the specific numeric types you're working with. This shift lets you focus on algorithms as first-class concepts rather than just on type constraints. Absolutely. Let's look at a simple example using CH11's more generic numeric approach. In earlier versions of C#, you might write a numeric algorithm that works specifically for int or double. For example, a simple summation function might like this. Public sum integers, enumerate in numbers, I get sum, and then over time I may want to blah blah blah. And for doubles, you'd need a separate method. And then I maybe want to sometimes do some doubles. In CH11, with generic math support, you can define a single method that works for any numeric type that supports addition. Here's how you might do it. Using system numerics. Public sum numbers t, where t is I number of t, t minus 0, and you add more number. In this example, t can be any numeric type that implements the I number of t interface. That means you can call some numbers with integers, doubles, or any other numeric type that fits, and you only need to write the algorithm once. So the big takeaway is that CH11 lets you think more in terms of general algorithms rather than having to tie yourself to specific numeric types. It's more flexible, keeps your code dry, don't repeat yourself, and maintains all the type safety and performance benefits you need.
Practice Prompt 4. Required members and honest objects. Ask your AI assistant. Before C#11, why was object construction fundamentally dishonest? How do required members change the lifecycle of an object? Focus on partial initialization, invalid but constructible objects. How the compiler now enforces invariance. Outcome. You should be able to explain how object validity becomes explicit and verifiable.
Sure. Before C#11, object construction could be a bit dishonest because you could create an object in a partially initialized state. In other words, you might instantiate a class without setting all the properties that really should be set for the object to be valid. This meant you could end up with objects that technically existed but weren't really in a valid or fully usable state. With C#11 and the introduction of required members, this changes. Now you can mark certain properties as required, and the compiler will enforce that these members must be initialized when you create an object. This makes it impossible to end up with an object that's missing those crucial pieces of data. In other words, object validity becomes explicit and verifiable at compile time. The compiler itself helps you guarantee that your objects are always fully and honestly constructed. Absolutely. Let's look at a simple example to illustrate how required members work in C#11. Before C#11, you might have a class like this. Public class person, whose name you have to set, and maybe an age. We could create a person without setting name or age. The person without name. This is allowed, but not very safe. Here, person can be created without a name or age, leading to an object that isn't really complete or valid. With C#11, you can use required members. This person must have required string name in it, and this person must have age in it. Now the compiler enforces you must set name and age when creating a burden. Age 30. This is required and safe. In this example, if you try to create a person without providing both name and age, the compiler will give you an error. This means the object is always fully and honestly constructed, making its validity explicit and verifiable right at compile time.
Practice Prompt 5. Struct safety and default values. Ask your AI assistant. Why are default values dangerous for structs? How do auto-default structs reduce semantic risk? Focus on default, T, and invariant violations. Why structs were historically fragile. How C#11 aligns value types with safety expectations. Outcome. You should understand why safer defaults matter even when code compiles fine.
Sure. The idea behind this prompt is to explore why default values in structs can be a bit tricky and how newer versions of C# improve that. Traditionally, when you create a struct in C#, it gets a default value, like all fields set to 0 or null. This can sometimes cause problems if those default values don't make sense for the logic of your struct. Basically, it can lead to situations where the struct is in an invalid state by default. In C#11, there are improvements that help align value types with safer defaults. Essentially, it reduces the risk that you'll end up with a struct in an unintended or invalid state just because it was automatically given default values. So even if your code compiles and runs, having safer defaults helps prevent subtle bugs and makes your structs more robust in practice. Absolutely. Let's look at a simple example to illustrate the idea of default values in structs and how C#11 helps make things a bit safer. Before these improvements, you might define a struct like this. Public struct point has int x, int y. When you create a new point without assigning values, it'll default to 0, 0. That might be fine in some cases, but in others, a default value of 0 might not make sense for your logic. For example, you might want to ensure that a point is always initialized with valid coordinates that you explicitly provide. In C#11, you can use features like parameterless constructors for structs. This allows you to define a struct that can enforce certain initialization rules, making it safer by default. Here's an example. Public struct safe point. My x is 0, while y is 0. Parameterless constructor that enforces some default logic. ix equals -1 or any invalid default that makes sense for your logic, and y equals 10. And public structs where you can implicitly define safer initialization rules, making safer defaults whilst also making code more robust. Instead, in my default to -1 or whatever you decide is a clearly invalid state. This makes it obvious if you forgot to initialize it properly. In other words, by allowing parameterless constructors and similar safety features, C# 11 helps you reduce the risk of having structs in an invalid or unintended default state. Makes your code more robust and helps prevent bugs that can come from unexpected defaults.
Practice prompt 6. List patterns as data validation. Ask your AI assistant. How do list patterns change the way we reason about collections? Why is this about data shape, not control flow? Focus on matching structure instead of looping. Declarative validation. Reducing index and boundary bugs. Outcome. You should see pattern matching as data reasoning, not syntax sugar.
Sure, this practice prompt is about understanding how list patterns in C# change the way we think about collections. Instead of using traditional loops to check elements one by one, you focus on matching the structure of the data in a declarative way. This means you're describing what the data should look like rather than how to iterate through it. The key points are, you're matching the structure of the collection directly rather than using loops. This is more about validating the shape of data than controlling the flow of your code. It helps reduce errors related to indexes and boundaries because you're not manually indexing collections. In the end, you should see list pattern matching as a way to reason about data itself rather than just a syntactic convenience. Absolutely. Here's a simple C# example that uses list patterns for data validation. Queuing system. Okay, my numbers are 1, 2, 3. Using a list pattern to match the shape of the array, if numbers is exactly matches 1, 2, 3, or if numbers is 1, all of course starts with 1 and ends with 3, with any number of elements in between, or else the array has a different shape. In this example, the first pattern 1, 2, 3 checks if the array matches exactly that sequence. The second pattern 1, all uses the ... pattern to match any number of elements in between the first and last elements. This way you're validating the structure of the data directly without looping through the array manually.
Practice prompt 7. Strings that look like strings. Ask your AI assistant. Compare raw string literals with traditional string literals. Why is this a real-world improvement, not just nicer syntax? Follow-up prompt. When would UTF-8 string literals matter in real systems? Focus on escaping versus readability, templates, JSON, SQL, and protocols, allocation and transcoding costs. Outcome. You should understand why strings become clearer and faster in C# 11.
Sure, let's break it down in English. So the practice prompt is about comparing raw string literals with the traditional string literals we've always had in C#. Raw string literals are basically a new feature in C# 11 that let you write string that look more like what you intended without having to escape things like quotes or backslashes. This is a real-world improvement because it makes code that includes things like JSON, SQL queries, or other templates much more readable. You don't have to clutter your strings with escape characters, so it's clearer and easier to maintain. The follow-up question about UTF-8 string literals is about performance and efficiency. In real systems, if you're dealing with a lot of text processing, using UTF-8 string literals can reduce allocation overhead and transcoding costs. Basically, it can make your strings not only clearer, but also faster and more memory efficient. So the outcome is that with C# 11, you get strings that are both easier to read and more efficient to use. Absolutely. Here are some C# examples to illustrate both raw string literals and UTF-8 string literals in C# 11. Okay, raw string literals example. Let's say you have a JSON string. In traditional C#, you'd have to escape quotes and line breaks. With raw string literals, you can write it exactly as it looks. Or traditional string literal, string traditional JSON is to just -name. Raw string literal C# 11 is 3 dots. Okay, raw JSON. In the raw string literal, you don't need to escape the quotes. The string looks just like the JSON itself, making it much more readable. 2. UTF-8 string literals example. In C# 11, you can use a U8 suffix to indicate that a string is a UTF-8 literal, which can be more efficient when you're dealing with a lot of text processing or specific protocols. Traditional string, UTF-16 by default, string default string, hello world, UTF-8 string literal, read-only span of byte, into the U8 suffix. The UTF-8 literal can help reduce memory usage and improve performance in scenarios where you need to deal with a lot of strings or communicate over protocols that prefer UTF-8. In summary, these features in C# 11 make strings both clearer to read and more efficient to handle.
Practice prompt 8. Encapsulation at scale. Ask your AI assistant. Why do large codebases and source generators suffer from type leakage? How do file local types improve architectural hygiene? Focus on namespace pollution. Internal helpers versus public surface area. Tooling and generator correctness. Outcome. You should be able to articulate why this matters most at scale, not in demos.
Sure. So the idea behind this practice prompt is to understand why large code bases can run into problems with type leakage. Essentially, as a code base grows, you can end up with a lot of internal types that unintentionally become visible outside the places they were meant to be used. This is what we mean by namespace pollution. Too many types cluttering up the namespace and potentially making it harder to maintain a clean architecture. File local types help solve this by letting you define types that are only visible within a single file. That means you can have internal helpers that don't leak out into the broader project, keeping the public surface area of your code clean and well organized. In other words, this really matters at scale because, as projects grow, having too many publicly exposed types can make the code harder to navigate and maintain. By keeping things file local when they're not needed elsewhere, you maintain a cleaner architecture and ensure that tools and source generators work more predictably without accidentally exposing internal details. Absolutely. Here's a quick example to illustrate how file local types can help. Let's say you have a utility type that you only need in one particular file. Before C# introduced file local types, you might have something like this in a shared namespace. Namespace myapp utilities, internal class helper.static. This helper class is visible to the entire myapp utilities namespace. With file local types, you can define the type so that it's only visible within the single file where it's declared. For example, at the top of your file, you might write file class helper, public method do something. Now this helper class is only visible in this file and won't pollute the namespace. In a large codebase, this means you can create as many file local helpers as you need without worrying that they'll accidentally become part of your public API. This keeps your architectural boundaries cleaner and makes it easier to manage large projects.
Practice prompt 9. Span-friendly safety. Ask your AI assistant. Why is pattern matching over span less than char greater than against constants significant? What problems does it solve without sacrificing safety? Focus on zero allocations, safer parsing, compiler-assisted correctness. Outcome. You should see how performance and safety are no longer opposing goals.
Absolutely, let's break that down in English. So this prompt is essentially about understanding why using pattern matching on a span of char against constants is a big deal. In other words, it's important because it allows you to do efficient zero allocation checks on spans of characters, like slices of a string, without creating extra garbage or overhead. The problems it solves are mainly about performance and safety. Normally, parsing or checking strings can involve allocating new objects, which can slow things down and create extra work for the garbage collector. By using span char and pattern matching, you can keep things lean and let the compiler help ensure correctness at compile time, not just at runtime. The outcome you're aiming for is to see that you can have both performance and the safety together. They're not in conflict. You get the best of both worlds. Of course, let's look at a simple C# example that demonstrates pattern matching over a span of char with constants. Using system, I'm going to keep it in the US, but say we're going to try it out. So pattern matching on span of char against constant, string result is span which you entered yes, no, or unknown input. In this example, we convert a string to a span of char and then use a switch expression to match it against constant strings like yes or no. If the input matches yes, it returns a specific message, and the same for none. If it doesn't match, it falls back to a default case. This approach means you're not creating new string objects unnecessarily, and you rely on the compiler to ensure the matching is safe and efficient. It's a nice illustration of how you get both performance, no extra allocations, and safety. The compiler helps with correctness at the same time.
Practice prompt 10. Low-level power, explicitly scoped. Ask your AI assistant. Explain ref fields and scoped ref conceptually. Why is explicit lifetime control critical for low-level correctness? Focus on reference escape bugs, span-based programming, why power must be constrained, Outcome. You should understand how C# offers power without weakening guarantees.
Sure. So basically, this prompt is about understanding some advanced lower-level features in C# that give you more control over how references are handled. When we talk about ref fields and scoped ref, we're dealing with ways to explicitly manage the lifetime and scope of references. In other words, you're making sure that references to certain memory areas can't escape the scope where they're supposed to be safe. This is really important for low-level correctness. If you don't control the lifetime of a reference explicitly, you could run into bugs where references outlive the data they point to, causing things like memory corruption or unexpected behavior. By using scoped refs and ref fields, C# is giving you that low-level power while still maintaining strong guarantees about safety. You get to do more advanced things, but in a way that's still clear and controlled. Absolutely. Here are a couple of C# examples to illustrate these concepts. First, let's look at a simple example of a ref field. Suppose you have a struct that wants to hold a reference to some external data, but you want to ensure that reference doesn't escape in an uncontrolled way. Ref struct ref holder. I have a ref int. This is a ref field. My parameter ref, when I pass in a reference, is ref. It's super helpful to use ref correctly. In this example, ref holder holds a reference to an integer. Ref struct keyword ensures that this struct is stack only, which means it can't be allocated on the heap, and its references are tightly controlled. This helps prevent references from escaping the scope in a way that could lead to bugs. Now, for the idea of scoped ref, imagine we have a method that takes a reference and ensures it can only be used within a certain lifetime. Would process scope data? This data reference is guaranteed not to outlive the scope of this method. Data is data too. Here, scope ref is a conceptual example. The exact syntax may vary depending on the C# version that tells you this reference is only valid inside its scope. It won't leak outside, preventing bugs related to reference lifetimes. In summary, these features let you do powerful low-level programming in C# while making sure you don't lose the safety and guarantees the language provides.
Practice Prompt 11. Evolution Framework Evaluation. Ask your AI assistant. Evaluate C#11 using the evolution framework. Which changes are semantic, and which reinforce long-term maintainability? Focus on: what problems were solved? Compile time versus runtime guarantees. Why this version matters long-term? Outcome: you should be able to defend C#11 as a structural hardening release.
Sure. So this practice prompt is basically asking you to look at C#11 through an evolution framework, which means you're evaluating how the language has evolved and what kind of improvements it brings. When you're focusing on which changes are semantic, you're looking at changes that affect the meaning and behavior of the code rather than just its syntax. For example, if C#11 introduces new features that change how certain constructs behave at a deeper level, that would be a semantic change. On the other hand, changes that reinforce long-term maintainability are those that make the codebase more robust, easier to maintain, and more reliable in the long run. This might include improvements that provide stronger compile time guarantees, meaning you catch more errors before you even run the code, rather than relying on runtime checks. Ultimately, the outcome is that you should be able to explain why C#11 is seen as a structural hardening release. In other words, it's a version that doesn't just add flashy new features, but strengthens the language's foundations, making code safer and more maintainable for the long haul. Absolutely. Let's look at a few C#11 style examples that illustrate these ideas. 1. The semantic changes. One of the themes in C#11 is improving pattern matching and data flow analysis. For example, you might have more refined pattern matching that allows you to express conditions more clearly. If object is my type, property is greater than 10 and less than 20, this is a semantic enhancement. We can now express more nuanced patterns directly. Here, the semantic change is that you're capturing a more expressive condition right in the pattern, which makes it clearer and reduces the need for extra runtime checks. Compile time guarantees. C#11 continues to strengthen compile time safety. For instance, it might add more scenarios where nullability is enforced, catching potential null references at compile time rather than letting them slip into runtime. String possibly null, get nullable string. If possibly null is not null, the compiler can enforce more rule here, making sure we handle nulls correctly. This reinforces long-term maintainability because you're less likely to have null reference exceptions popping up later. Structural hardening. Finally, think of features that provide more robust defaults or stricter rules that prevent common pitfalls. For example, imagine C# 11 introduces more ways to enforce immutability or to limit the visibility of certain constructors, making the code base more predictable and maintainable. Public class by immutable class has required int id get init, and name is name. My immutable class is constructed like this. By requiring certain properties at initialization and using init-only setters, C# 11 helps ensure that once an object is created, it remains in a valid and stable state. This is a form of structural hardening. In summary, these kinds of samples show how C# 11 isn't just about new syntax, it's about evolving the language to solve real problems, add stronger compile time guarantees, and make code bases more maintainable in the long run.
Final reflection prompt. Ask your AI assistant. If C#10 improved defaults, how does C#11 redefine what correct code means? Outcome. You should clearly articulate why C#11 makes the compiler a guardian of intent, not just a translator.
Sure. This final reflection prompt is basically asking you to consider how C#11 changes the idea of what it means for code to be correct. While C#10 focused on improving defaults to make code clearer and more maintainable, C#11 goes a step further. It makes the compiler act more like a guardian of the programmer's intent. In other words, C#11 isn't just about translating code into machine instructions, it's about ensuring that the code you write expresses your intentions clearly and safely. By doing this, the compiler helps prevent entire classes of errors and make sure that the code is not just syntactically correct, but also semantically aligned with what you intended to achieve. Absolutely. Let's look at a few examples to illustrate how C#11 can redefine what correct code means. Init-only setters and enhanced immutability. In C#11, you might rely more on init-only setters to ensure that objects are only set at construction time. This means the compiler enforces that certain properties can't be changed after an object is created, making your intent clearer. Public person, I want my name to be in it. What's considered as correct code? Yeah, code that prevents anything changing. After construction, person.name.age cannot be changed. Pattern matching enhancement. C#11 might introduce even more refined pattern matching capabilities, allowing the compiler to ensure that all possible cases are handled. This reduces the risk of unhandled scenarios. Public shape describe shape is a circle with etc is false. Rectangular rectangle ra is equal to width and height. The compiler ensures all patterns are considered, reducing logical errors. Enhanced null state analysis. C#11 continues to improve the compiler's ability to analyze nullability, meaning it can catch potential null reference issues at compile time rather than at runtime. This helps ensure that your code is correct by design. String may be null. Get possibly null string. If maybe null is not null, compiler knows maybe null is not null here, making it safer. Console white line may be null length. In all these examples, the compiler in C#11 is more proactive about helping you write code that truly reflects your intentions and avoids common pitfalls.